everybody, and welcome to today's HoliSoils webinar on forest soils mapping and monitoring. Before we start, you can ask questions at any time, but please write them in the chat function. You find this on the bar below, and we will answer them all at the end together with our two lecturers. So before we start with the content, I will introduce you to our lecturers. It's Stephan Mantel and Laura Poggio. Both are working for ISRIC, the World Data Center for Soils. And first, Stephan, he is a soil scientist working as the head of the World Soil Museum. And I had the pleasure of meeting him last year at the workshop, and he is really an expert on worldwide soils, and I'm really glad that we have him here to share his experiences with us in his part of the talk. And afterwards, Laura Poggio, she's a modeler and she's specialized on digital soil mapping, has a focus there on soil-climate interaction, which is getting more and more important, as you probably all know. And within HoliSoils, she created soil property maps. And so I think she's really the perfect person to tell us more about the mapping of soils later on. And with that, I will give the words to Stephan and his part of the talk.
Thank you, Vera. I will share my screen now. Here. Can you see my full screen? Okay.
It's not yet in presentation mode, but I see that there's a loading sign.
Let me check. Is it better now?
Yes.
Okay. So, yeah, I will talk about forest soils and aspects of management, and also spatial planning related to forest management. Yeah, as Vera said, I'm Stephan Mantel. I work for ISRIC, but I've also been involved in forestry projects in the past, especially in Southeast Asia, related to sustainable forest management. And the final part of my presentation, I will give a few examples of those, how soil information and landscape information can be an input to sustainable management planning of forests and plantations. So what I will talk about is are the forest soils in the world, and the major soil groupings. I'll use the WRB International Classification System as a guideline for that, so I'll use those terms, but I'll explain them. And I give some examples about major soil groupings on the forests, and then I'll talk about some some of the projects I've been involved in on sustainable forest and plantation management. Yeah, so the global forest cover. This is one map I could get my hands on about forest cover. It's probably not up to date, but it gives us an idea about where forest can be found in the world. So in the Northern Hemisphere, on the tropics, and we overlay that with the soil maps of the world with the major soil groupings. So the 32 units of the WRB, which identifies soil units with distinct properties and functions. And then when you look at what overlaps with the forest, you come to a certain level of grouping and dominant soils within the forest zones in the world. And then when you look at the table of that, you see that certain soils dominate. Mostly they are poor soils or tropical weathered soils. And of course, when human population and also agriculture expands, then forests are more retreated towards the more steep areas in the world, and also maybe less favorable soils for agriculture. And I will discuss briefly the four soils of this list from the dominant part: the podsoils and the leptosoils, which are also found or dominantly found in the temperate zone of the world, and then two tropical soils from the tropical belt, the fertile soils and the acri soils. So a few examples, those 4 soils. The pot soils are soils from sub-humid to temperate climates, and they're mostly often found in mountains on sandy deposits. So they are soils in siliceous parent material, and yeah, there's a specific soil process that has formed them, colluviation. So that's the movement of metal humus complexes downward in the profile, depleting the upper zone and enriching the lower zone with these complexes of iron, aluminum, and organic carbon. And well, as I said, they occur in a specific climate, humid, temperate, and boreal regions of the northern hemisphere, and in level to hilly land under heather. So and also specific vegetation, so pine trees, heather vegetation, which also adds to the acidity of the soil. And then that accumulation zone is the spotting horizon. So this is what the profile looks like. You have accumulation zone, the O horizon, so the forest litter layer or the heather litter layer. And then below that is the depletion zone, the E horizon. It's albic material, so white material depleted of the iron and organic matter complex, which precipitates in the BHS, so the subsoil below, and below that you get transition to the parent material. So pot soils have a sandy texture. They have weak aggregation into structural soil elements, so low aggregates stability, low water holding capacity, and also because of this movement of iron, you may get an iron dense subsoil, which also may be impermeable to water. So in those areas you may find also standing water or water pools, even though it's very sandy soil, but that's because of the iron concentrated in the lower part. And it has an obviously low fertility because of the high silica content, low buffering capacity for nutrients, low nutrients containing. And this is an example of a pot soil landscape in Brazil. You see shrub vegetations and poor vegetation diversity, also degraded soils in the front, so they're easily disturbed. And in the tropical areas of the world, you have the same processes, but they go much faster and much more intense because of the higher temperature and climate. These processes are accelerated, and you get very deep E horizon, so this depletion zone, into areas with meters and meters of these bleached sands, which are almost pure silica. So it's a party for the glass industry, because they can mine this and get glass out of it from these completely depleted zones. So yeah, especially in sloping areas, these soils need to be carefully managed for timber harvest, for instance, to keep soils much covered, and careful with machinery access. And upon degradation, vegetation recovery will be very poor. So next logging cycle will be very difficult. Pot soil distribution, I already told you where they are. Here you see that exemplified in a map. So especially in the northern hemisphere, with some areas in the tropics where there's sandy parent material. Then leptosols. Leptosols are shallow soils, the order of the shallow soils. They may be either very stony with little fine earth, or very shallow by nature. Leptosols often occur in mountainous areas, but they're found in all climate zones. And they're very shallow. That's their definition, or extremely rich in coarse fragments and stones and rocks. So this is an example of a leptosol. This is from Jordan, where you see almost 15 centimeter of soil overlying parent material. There were trees and even a crop on this, wheat, and then the tree crops were olives. So it's still possible to farm, but yeah, it needs special management. And this is a skeletal soil with high content of rock and rock fragments. Leptosols is the shallow soil class. It can be even shallow as 0 centimeter. That also is classified as shallow soil. So this is a nudilithic leptosol, nudi for bare, lithic for rock, and then leptic is of course shallow. So leptosols in general free draining soils, and they are defined by the shallowness or stoniness. Erosion is the major threat to leptosols because they're often in sloping positions and they're already shallow. And of course, disturbance must be minimal upon managing these soils or using these soils. and they occur everywhere in the world. They are the dominant soil of the world because we have many sloping areas. So they can occur across climate zones and landscapes in the world. Now, then to tropical soils. We have tropical soils occur often on around the equator, of course, and they are characterized by they are formed and characterized by intense and deep weathering, strong leaching, often have high biomass production, and well, they're often deep soils because of often they are also part of these tropical soils are found on old parts of the earth crust, so they've had long time to develop. Their clays are often weathered. They're calanitic clay, which means they have lost their capacity for buffering to a great extent. Soils have a net negative charge, the cation exchange capacity. So in calanitic clays, this is much reduced. And therefore, they also have a low nutrient retention and inherently a low level of nutrients. Often strongly acid, so the buffering capacity is dominated by protons, so acidity and high levels of aluminum saturation. And their main components are sesquic oxides and hydroxides. So these are iron and aluminum oxides and hydroxides. They often have high biological activity, especially ants or termites, and a high rate of organic matter turnover. Well, this is a picture from Kenya, a forest on feral soil, so a typical tropical soil. So talking about the feral soils, they're strongly weathered, yellow and red tropical soils. The yellow more on the wet side of the tropics, the red where there's a bit of a dry season. So the yellow soils are more from the Amazon, for instance, and have a high content of sesquic oxides. And they develop on these old, stable geomorphic surfaces, and more even so, they are developed faster in basic rock than in rock from siliceous material. And this is a typical image of a feral soil. It has very poor or low macrostructure, but very high microstructure. So strongly aggregated clay minerals together. And they have different forms, yellow and red, depending on the domination of the iron or aluminum oxides and hydroxides, and that's dependent on the amount of rainfall. They're very difficult to manage because they have a very low nutrient reserve. Feral soils can have a net zero charge, which means they cannot buffer nutrients. They cannot hold them except for the organic matter content they have, because organic matter also supplies a charge. So and they're deeply well drained. The high iron content means that they are high in fixating phosphate to the extent that vegetation cannot take it up. So that's the main limitation. They have good physical properties, they're stable, but they have, not a very bad, but a rather limited capacity to hold available water. So in management, the prime aspect is management of organic carbon. They can be high in organic carbon, but it's because that's then also the main source of soil fertility and the buffering capacity, but therefore with intervention or plantation management on feral soils, the maintenance of the protected cover and conservation of the topsoil is crucial. And termites are a source for soil fertility, so conservation and preservation of termite hills is also important, as other also ant heaps. You see they're mostly around the equator, and that's where they are found, and that's obvious. HoliSoil is a related soil. It has a clay eluviation layer, so clay moved from the top to the down to the subsoil, but it's a tropical clay, so a low buffering clay, low cation exchange capacity. Here you see a slash and burn plot, which is typical for use of HoliSoils in rainforest conditions in Poggio. And they occur also on old land surfaces with hilly or undulating topography in regions with a wet tropical, monsoonal, subtropical, warm tropical, temperate climate. And forest is the natural vegetation type. And they are characterized by these properties of the clay, as I just mentioned. This is a typical profile. So you have the O horizon, so the litter layer, the forest litter layer, then you get depletion zone, the E horizon, a transition horizon, and then you get the accumulation zone of clay. And in these soils, since clay has moved downward, the top of the soil has lower clay content, more silt content, which means lower aggregate stability, more susceptibility to erosion and crusting. And that's important for management as well. So overall, the chemical properties are poor. They have low levels of plant nutrients and mineral content. They have high aluminum toxicity, and the P sorption is also strong because of also the presence of these sesqui oxides, these oxides and hydroxides of iron and aluminum. Topsoil slaking and crusting is quite common when they are bare, and because of this low structural stability, it can cause massive soil erosion after land clearing. I'll show you a picture in a moment. So also for management, same as with ferrous soils, the organic carbon content of the topsoil is the prime source for soil fertility and the buffering capacity. And also their topsoils are easily eroded, so the topsoils need to be conserved and preserved. And any intervention in forest on agri-soils must consider this preservation and conservation of the topsoil as much as possible. So selective felling is then one practice in sustainable forest management, and avoidance of heavy machinery also taking logs from one place to another place, which damages the topsoil. And after forest logging and forest degradation, plantation and agroforestry management are good alternatives to keep the soil covered. And again, here termites are a source for soil fertility, so conservation of the termite heap is important. And here you see the distribution of agri-soils. They occur a bit more broader from the tropics than ferrous soils, but mostly they are concentrated around the equator. Okay, so these were the 4 of those 32 major soils that are relevant for forest or occurring in forest. And I would like to show you some examples of forest and plantation soils and management. The first one is a simple one from the Mato Grosso, Brazil. Plantations often look for to establish a plantation. People look often for flat areas, accessible, preferably near rivers or roads and access to cities. And you had a time when there was a preference for or investment in teak plantations, so that over 40 years your share in teak would be awarded with the growth of the teak and the sale of the timber. But often plantations, they are established on poor soils because, flat areas, accessible, are not easy to find. Let's say those that are not in use are not easy to find. And you saw here that the trees are green, but the trees are relatively thin. And after a few years, then the plantation looked quite, not so nice because of shedding leaves, and also the tree trunks were still thin. And only afterwards, soil research was done, and then it was noted that they were dominantly on plinto soils. And plinto soils are soils with high accumulation of iron components in the subsoil, which harden when the soil is dried. It's getting drier. So then in the establishment stage of the plantation, the trees are still fine because they can extract enough water and nutrients from the first half meter. But then when the trees grow, they need more water, more nutrients, and then the trouble begins, which is very difficult to repair because then you need for the lifetime of the trees to supply water and nutrients. Good, then last example is about planning of sustainable forest management and spatial planning in a forest concession and also in a larger area. This is an example from Indonesian Borneo, so Kalimantan, where the forested land is under pressure from various directions. You have intrusion of farming into forest, you have forest fires. There are many precious minerals below the forest, so coal and other minerals, iron and mining, and then illegal logging, and also clear cutting and plantation development, oil palm, for instance, but also other plantations. So the pressure is high, and the soils the dominant soils in Indonesia and Borneo are these agri-soils, which I just explained. So on the top they have a silty, low aggregate stability, and the dense clay subsoil in the lower part, but that is acid and aluminum saturated. And they are often on slopes, which means that erosion is a real threat. And when you remove the vegetation, this is an image taken a few weeks or months after logging, and you see that the pillars there are the former subsoil. They are exposed, and they are acid and aluminum toxic. So forest regeneration is very unlikely on this eroded soil. So thinking about economic management of a forest concession, and mind you that in Indonesian Borneo, and that was the whole surface. 80% of the whole surface was given out in concession already in the 1980s. So if we think about, if we prefer to have the forest function maintained over time, you need to think about sustainable forest management. So logging as one of the activities, but then done more sustainably. And we worked together in a European project with among one of the larger concession holders. You see that here in the map. And there was extensive work done on the field information gathering. So the soils were inventoried, landscapes, altitude, but also the vegetation, the vegetation, the timber species, etc. And then we made maps based on the database that was developed. So for instance, also where a rattan will likely occur or grow. But also the volume, the timber potential was done by the vegetation specialists. And then we applied models to the area of the concession, erosion risk with and without vegetation. And from that difference, you can have an indicator for the impact of removal of vegetation. So the sensibility of the terrain for erosion and ultimately linked to the potential for regrowth. And made an ecosystem stability map. So where would intervention be more serious than in other areas, which areas are stable and which areas are sensitive to intervention. Also, the biodiversity in terms of flora and fauna were inventoried, what are hotspots within the concession and what are less biodiverse, to take into account of which areas you should set aside and conserve, for instance, a seed bank. So ultimately, that came to a map which would be a planning map for forest management. So the red areas would be better left for nature conservation, also serving as a source for biodiversity and forest regrowth. And the green areas would be stable enough to do selective felling and forest timber production. Now, that we also did. At the time, there was a decentralization, so there was a big demand for giving out concessions by the local district, the district leaders, and they needed information. So they asked, can you upscale this map, for this concession, to the district and later to the supra-provincial area? So we used then different layers: the state forest land, what is inside or outside state forest land, the potential risk maps that I already showed, conservation status, some areas already identified as conservation for long term, critical and fragile lands, like this ecosystem stability map, production status determined by land cover, the ruggedness of the terrain, and the protection factor. So all these layers were overlaid to produce a land use planning map, or forest management zonation, I should say. And so what we did for the concession was then upscale to the supra province level, as a input to planning for where, if you want to put priorities for conservation and for production, to have a choice, a better founded choice, let's say. So that's an illustration of how land type and also soil information can be an input to more sustainable management decisions. And that's the end of my presentation. Shall I stop sharing?
Yes, thank you, Stephan. I think if there are questions, people can put it in the chat and we will answer them later on. So far, there are no questions, so very good job. Everything is clear. And I think now we're heading over to Laura. And yes, thank you, Stephan.
You're welcome.
Thank you, Vera. I hope you can see my slide now. They should be into presentation mode. So today I'm going to present a bit about the challenge of mapping for soil for Europe. These, as Vera said, were mainly activities done within the context of HoliSoils as supplement of some of the mapping activities that are happening at ISRIC as well. So the first is why we need soil maps specific for forest soils. Generally speaking, soil property maps provide essential information for forest management that are important to have. And they help complementing information on resource, forest ecosystem, hydrology to support decision making for the management of the forest itself. And also soils are really important to the provision of the ecosystem service in general by forest as well. So we produce map of certain soil property with their uncertainty, because if we want to use these maps in further modeling, the uncertainty and know how much we can rely on them in different areas is quite important. We use a digital map soil mapping approach, and this is a very brief introduction to this. The main ingredient of the digital soil map approach are four, in my opinion, that are the soil observation, very important. These are observation in the field with physical, chemical, and more recently spectral analysis. And without those, we cannot produce maps. Then we use covariate or environmental layer that explains the relationship between the soil and the landscape and the ecology of the area. And then we use a model, predictive model, that can be of different flavor. It started as geostatistical, and then it moved more in the direction of machine learning AI models. But the main principle is that predictive model explain the relationship between the training data and the covariate, and especially allows to capture the variability and the spatial variability in the fields. And then we have our maps, but we need to do an evaluation. We need to assess how accurate these maps are, what is their uncertainty, and how well these maps represent the reality of the landscape in the field. And these has different approaches based on if we use continental map, like for the whole of Europe, like in HoliSoils, or if we use this approach for very localized activities like precision farming or precision forest management in catchment or other small areas. And in order to have the input data, a lot of work goes into cleaning, harmonizing, and standardizing those, and making them available for the users. So this is the general workflow of VOSIS, that is a soil observation database hosted at ISRIC that provides really a cleaning and harmonization of the data. Different methods, different depth, different approaches are harmonized for the user to be able to use that in various activities, including soil grids. In the course of HoliSoils, there was a lot of these activities done for a certain number of datasets that were shared during the life cycle of this project to increase the number of observation that VOSIS has on forest soils. And these are some of the examples that we do it. So we consistent checks, license, georeferencing. Do we have the right covariate, coordinate in the right place? Duplicate profile, checking for analytical procedure and units. And also we need to check fitness for intended use. Often we have users that are trying to share dataset with a positional uncertainty of 16 kilometers, and that is a bit much for when you're trying to make a map of 100 meters. And we are trying to develop method to deal with this, but there is a limit of wishful thinking sometimes as well. So we received a lot of dataset, about 7,000 profiles from 4 datasets, and open license means that they're fully served on the VOSIS. Restricted license means that they could only be used for HoliSoils activities. The challenging positional accuracy was for this project up to 4 kilometers. That is still better than 16, but is quite a bit. And this addition is about 7,000 profile for 230 million hectares of forest soil, so a density of about 3 point every 1,000 kilometers. That's not that great. So this is the dataset. We got a lot of information from the Scandinavian country, but also Germany and France and other countries. But this is improving a lot because we in VOSIS, there were already other data from these countries, and going from 20,000 to 27,000 is a big improvement of almost 1/3 of the observation. So this allowed to cover quite a bit of the forest area in Europe. But then soil is a three-dimensional body, is not just the surface. And these are the depth interval according to some international standard used often in digital soil mapping. And when doing the analysis for a property like soil organic carbon, that is one of the properties that has most of the observation, came that's basically we didn't have many observation below 30 centimeters. From the interval from 30 to 60, we had 94 points for the whole of Europe, and below 60, we had none. And this is interesting because, of course, sampling the topsoil is easier, but the soil doesn't stop at 30 centimeters, especially not the forest soils, and it's important to capture all of this. So we tried to do some modeling with this data. We collected covariate for the whole of Europe, representing the main soil forming factor, climate, organism and land cover, relief, parent material, and we don't have many information about time. So for climate, we use remote sensing, climate model, local meteorological dataset, relief, digital elevation model, and various parameters. For organism, we use remote sensing, derived vegetation index, land cover, some radar remote sensing, and some vegetation soil water indices. For parent material, this is always tricky. Even in Europe, there isn't a good geological map at the resolution and scale needed for 100-meter resolution maps. And we integrated it with some radar remote sensing. And it's a combination that often provide quite good results. So here are just some of the covariate that we used and that covers most of Europe. And then we did a map of 100-meter for Korean classes, because at this time we didn't have more refined forest map of Europe, and we use the maps of the mean and the median using quantile regression forest, and then we use the quantiles to use the interquantile range as a measure of the modeled uncertainty. And I'm going to present the result for the topsoil, the 0 to 30 centimeter. We consider primary property, organic carbon, inorganic carbon, pH, nitrogen, coarse fragment, texture, sand, silt, and clay, bulk density, and we try to model some of the stocks. And of course, for each of them, we have uncertainty and accuracy. This is a preliminary analysis of the accuracy of this property. We got some quite decent result. The model efficient coefficient is a similar matrix to the R-square, with metrics that are online for continental and global, beside carbon and nitrogen that are pretty low metrics. And here we have some of the maps. They represent only the forest soils because we fitted the model only for forest soils, and this improved the result already quite a bit. We have the pH, we have the nitrogen, and we have the carbon, and all the other properties that are mentioned are also available in the project portal hosted by Thünen and as web services as well from ISRIC infrastructure. And then we did the uncertainty index. Here you can see more how scattered is across because we only consider the forest soil. And finally, we also assess the area of applicability, so seeing where the model extrapolated versus where the model really learned something from the data. And you can see that the density of the point is quite an indication of how well the model that we use learned the covariate relationship is representative of a certain area. So one important measure is the stocks, and we try to model that both soil inorganic stocks, soil inorganic stocks, nitrogen stock, and soil organic carbon stocks. And the results are a bit low, especially for soil organic carbon stocks. And yeah, the maps are also a bit misleading, especially for not misleading, it's strange pattern for forest soil experts, because we have kind of lower stocks in the Boreal region than in the more temperate region. And this is for a good reason, that we couldn't use yet the surface organic layer for this, because there are a lot of inconsistencies and difference between country and classification system. We know it's potentially a huge pool of organic carbon, especially in the boreal and north temperate forest, but we also lack the density data to calculate the stock. So we have the organic concentration, but then we lack the density to get to the stock. So we are still working on this, because we want to provide maps that are consistent and that are complete, and the full comparison with the uncertainty propagation and the impact assessment will follow in the publication that we are still working on. So as concluding remark, we compared also HoliSoil with all other soil organic maps generated in the framework of several European scale projects, like AGP, Cap4Soil, ESA, WorldSoil, Soil Grids, and we found that there are still a relevant difference in the estimated property and in their spatial distribution. These need to be further investigated. We're finding out that the combination of covariate and input points sometimes create a similar model but a different maps, and these need to be addressed, especially when multiple European projects produce similar maps. But for HoliSoil, we have up-to-date soil property map for European forest soils with uncertainty. We achieved the integration of the different data set at continental and national level. We need more deeper soil observation in forest region and more information on the organic layer. And we have products that can be used in vulnerability model and climate change scenarios. And we are planning on improvement for the stock estimation depending on data availability and suitability for this type of assessment. So thank you very much, and this is for my slides.
Thank you, Laura. I think this was very interesting, and also something that I really take with me from the HoliSoils project. We see the importance of the organic layers, which is what forest soils differentiate from agricultural soils, the organic layer. And also that harmonized methods over Europe are quite important, not just for comparing data with other neighboring countries, but also for making maps.
It's a good take-home message.
Yeah. But before we come to the take-home message, we have 2 questions currently in the chat. I think both are for you, Laura. I'm going to read them to you, and then you can answer them. At first, for soil data clearing and quality control, have you experienced any challenges within the standardization of analytical methods and units of measurement?
The short answer is yes. This is not really my area of expertise or work. I work closely with the two colleagues mentioned in the slide, Nils Bastius and Luis Calisto, on this, and I know that they had quite a bit of headache for many of datasets, not specifically for HoliSoils as far as I remember, but this is a hot topic and a big problem because different countries measure the same property in a different way, and sometimes the same country measure the same property in different way depending on the year, the institutes, or even the purpose or the project. So this is important, and I think that there is a lot of work going on trying to align methods, or at least come up with kind of lookup table which method is most similar to others. And I think this contributes also a lot to the uncertainty and to the issues that sometimes we see with the maps, because if the observation is already not very certain and then we link it with environmental layers, but we link the wrong value, then all of this propagates down the line.
Yes, that's also what I see from the practical part of the work. I mean, in the last 30 years also, the methods changed so much and the accuracy of measurements changed so much. And now to make consistent maps, we have to bring it all together. And this is really a challenge. And I'm glad that I do not have to do that. And I'm really like stunned by people who can do that.
I agree completely, and also a lot of challenges now with spectral measurement, because then is a kind of another model on top of the both lab and mapping models. So this is, I think, is going to be a challenge, and also a challenge to communicate to the stakeholder all of this.
Yes.
The map is not simply the value,
Yeah.
and the value is the truth.
Okay, the second question. Did you use or plan to use forest management plans from public enterprises to get more information about forest vegetation and some basic soil characteristics?
We didn't use those. There is no short-term plan, also because the project is kind of finished, but this will be really useful. And I know that both for forest and other sector, there is a lot of information hidden in reports and this type of plans, and it will be really good to get it out and start using it. I think that will contribute a lot to our efforts. I know of a case in Canada that they're planning to look at environmental reports to get information, and I know in Scotland they did for peat, to go through the environmental assessment of setting up wind farms to try to collect this information. But it's a huge effort that probably lies more with the countries or the regions or something like that.
I see the big challenge here that there is so much information. Like in Germany, this is organized on a very, very regional or local level. So you have you would have to go through lots of those management plans. And just for one country alone, not speaking about whole of Europe. So, I mean, maybe this is a federal state problem, but still a lot of work, a lot of information, and then, of course, a lot of people that have to work just for that before getting started on the rest of the mapping work.
Yeah, I agree. And I saw initial test on really using the large language model type of AI for this. And it was working decently well in English-speaking countries, but then as soon as you start to throw in other languages, then you need also a lot of fine-tuning for that.
Yes, yes, that's definitely a problem. And I can say that in Germany we're working on this, that we're getting more English documents there, because if we want to connect with other countries, it's important to have like common documents, not just those management plans, but in general, like also telling people how our inventory is done, like really those basic things. If you want to compare data to each other, you need to know the methods, and yeah, language is one of the bigger barriers there. I know that I searched for, I think, the threshold between litter and deadwood in France, and I learned French at school, but it's like 20 years ago, and it was quite hard to find that threshold. And it's just one thing I needed. So yeah, language as a barrier, but hopefully AI will do something positive there in the future.
Yeah, that will be, I think, a good use of these models if they can help summarize all this information.
Yeah. So we got another question. It's do you have forest soil carbon stock map of whole Europe available?
Yes, 0 to 30 centimeter.
Yes. I think I have the web portal link. I can put this in the chat so people can look up your maps there. There you can find all the maps that Laura showed in her presentation and explore them. Yes. So I think for now, those were all the questions. I think if further questions occur, people can contact you and us in the future as well. Thank you, Stephan. Thank you, Laura, for your nice talks. I think this was quite interesting. And before we stop here, I just wanted to tell our audience about the next webinar date. It will be on 5th of December, World Soil Day. And we will have a talk about more experimental fieldwork by Anni Palvi and Boris Tupek. They will talk about nitrogen fertilization experiment in boreal forests. And I hope to see you there all, and have a nice evening.